Hello dear students, welcome to Veda Gate Academy, your one and only destination for GATE and IAS coaching. Today we are going to start an important subject of ECE as well as electrical engineering known as signals and systems. So the subject what we are going to start is signals and systems. Why is this subject so important for ECE, electrical and instrumentation people? Because for ECE people, if I take ECE, this forms the basic foundation for the core subject of ECE, which is nothing but communication. Without knowing the basics of signals and systems, we cannot understand the subject called communication, which is a core subject of electronics and communication. Coming to electrical people, this subject forms the basic in understanding the core subject of electrical engineering known as power electronics. Power electronics. And coming to instrumentation people also, this subject aids in understanding communication, which is a part of instrumentation syllabus. So this is an important subject and we have to focus this subject in a careful way. And let me tell you, you can ask one thing, sir, what is the weightage of this subject? If we are studying this subject, or if you are sparing so much time on this subject, what is the advantage we are going to get? See, statistics say that based on the previous year statistics, we can say that on an average of 8 marks to 9 marks are expected from this subject. On an average of 8 marks to 9 marks are expected from the subject called signals and systems. And for electrical engineering people, you remember that if you want to get a good rank, first of all, what is a good rank? Good rank means a single digit rank or double digit rank. See, this subject forms or this subject plays a major role. So, if this subject is that much important, now we'll see what are the topics which we are going to study in this subject. Come on. See, this subject is divided into various units, of which the first unit, I'm going to divide the subjects into various units. First unit is signals. Signals. Second unit is systems. Third unit, LTI systems. Here, LTI stands for linear time invariant systems. And fourth unit is your Fourier series. Fourier series. Fifth unit, continuous time Fourier transform. Continuous time Fourier transform. In short, I can call this as CTFT. CTFT. In the sixth unit, we will be studying the applications of the fifth unit. Major application known as sampling. There are other applications like distortionless transmission, Hilbert transform, correlation, which we will be studying in the fifth unit only. But this is a major application, so I am going to take it as separate unit. After this, we will be studying discrete time Fourier transform. Discrete time Fourier transform. In short, we can call this as DTFT. DTFT. Eighth unit is your Laplace transform. Laplace transform. And ninth unit is Z transform. And the last unit, 10th unit, is DFT, which stands for discrete Fourier transform. And introduction to fast Fourier transform. Fast Fourier transform is removed from the syllabus, but anyway, we'll see some basics of fast Fourier transform also. So these 10 topics which we are going to cover in detail. Now you can ask one question, sir, is there any discount for electrical engineering students means yes, there is a discount. That electrical engineering students, you need not study the last unit. Discrete Fourier transform, simply you can skip. For EC and instrumentation people, all the units are there. But if a student says that, sir, he being an electrical student, sir, I am preparing for ESE exam, means you have to study the 10th unit also. So, electrical engineering student preparing for ESE exam, you have to study the entire units from 1 to 10. And one more thing is, for electrical engineering students, the 7th unit, discrete time Fourier transform, this will not be mentioned in the syllabus, let me tell you. They won't mention DTFT in the syllabus, but basics of DTFT are very much required for understanding Z transform. So I suggest all the electrical students to attend the 7th unit, that is discrete time Fourier transform also. So this is the sequence in which we are going to follow, and these are the topics which we are going to cover. Now, if this is the plan of action, why can't we start the first unit? Okay, let's start. Let me start the first unit, and before starting the first unit, okay, let me tell you one important point, that this subject, okay, this subject is like a chain. This subject is like a chain, means every unit will have a link with the other unit. See, if you want to understand systems, if you want to understand the second unit called systems, you must have a strong foundation on signals. Otherwise, you cannot understand systems, because we'll apply signals to the systems to achieve the required things. So, in order to understand systems, you must have a strong foundation on the signals. And if you want to understand LTI systems, that is the third unit, you must have a strong foundation on the second unit, because this linearity and time invariance will be discussed in the second unit. And if you want to understand the fourth unit, what is the purpose of Fourier series? It is used for representing the frequency domain representation of periodic signals. For that, you must know first of all what is a periodic signal, which will be discussed in the first unit. Every unit has a link with the previous unit. If you want to understand this continuous time Fourier transform, you must have strong foundation on the 4 units. Otherwise, you cannot understand continuous time Fourier transform. Or what I am saying is, this subject is like a chain, means every unit will have a link with the previous unit. So what I say is, don't break the chain. Don't break the chain. If you are breaking the chain, means very difficult to attach. Means you must attend the class regularly. You must attend the class regularly without fail. Then you can enjoy the subject like anything. So let's start with the first unit. Okay. So our first unit is what? Signals. Okay. Let me put the heading signals. %90 to 95% of the previous gate questions will solve in the classroom only, and will be solving many questions in every unit. That you will only see, that will be evident from the class only. Okay. First of all, what is the definition of it? In the first unit, the first and foremost definition you must know is, how do we define a signal? Or what is the definition of a signal? As we are starting the subject, our subject itself is signals and systems. No, first of all, you must know what is the definition of a signal. I can define signal like this. Signal is a physical quantity. Signal is a physical quantity carrying some amount of information. Signal is a physical quantity carrying some amount of information. This is a basic definition of a signal. If anybody asks you, what is the definition of a signal means, you must reply like this. Signal is a physical quantity carrying some amount of information. Then they will ask, what are the examples you can give for a signal? Yes, in the day-to-day life, we can give some examples like this. First example. Say you are reading a newspaper. We have some information about stock exchange. As the day is progressing, how the market is going to rise and how the market is going to fall. This is some signal which has some amount of information about stock exchange. Based on this, the investor, what he can do based on this kind of signal, he can take a decision whether to buy a share or to sell a share, because information is present here. In the same way, next example. Recently, elections were held in our country. Suppose if a political party wants to analyze how many Lok Sabha seats they have won compared to the previous years, they can analyze like this. In the year 2004, elections came. A particular political party got some 35 Lok Sabha seats. They were not satisfied with this 35 Lok Sabha seats. So they worked hard for the next elections, that is after 5-year term. So elections again came. They worked hard and they got some 52 Lok Sabha seats. Still they were not happy. Again elections came in the year 2014. They still worked hard. Got 75 Lok Sabha seats. Okay, they were satisfied. Again after 5-year term, elections came. Again this dropped down to some 27 Lok Sabha seats. 27 Lok Sabha seats. So again their performance got decreased. Now based on this, what is that political party doing? The leader of the political party, he can take a decision how to work for the upcoming elections, because information, their performance is present in the form of information here. So this is a signal, this is also a signal. Or in general, we can define signal as a physical quantity carrying some amount of information. Suppose there is a traffic signal. How many vehicles are passing through the signal in a day? If you want to record, that becomes a signal which carries some amount of information. Based on that, the traffic department can take a decision. How many babies are born in a town in a single day? If you want to record, that is a signal which carries some amount of information. How many corona cases are recorded in a day? That is a signal which carries some amount of information. Earthquake occurred in Indonesia. If you want to record the intensity of earthquake on a Richter scale, that becomes a signal which carries some amount of information. Or we say that the definition of a signal is a physical quantity carrying some amount of information. So your reply is, sir, we are confident with the definition of a signal. Now the next thing is, in how many ways we are going to classify these signals. Observe here. Or what are the various types of signals we have? Remember, these signals are classified like this. See, to classify any physical quantity, there must be some parameter, no? Isn't it? There must be some parameter. So these signals are also classified based on something known as dimension. Dimension. They are classified based on dimension. They are classified or categorized based on dimension, which stands for an independent variable. What I am writing here? Independent variable. See, what is this dimension? What is this independent variable? And what is the role of this independent variable in a signal? We are going to discuss now. Till now, we know only the definition of a signal. That signal is a physical quantity carrying some amount of information. Other than the definition, we don't know anything, right? Now we are going to classify signals. Now, what I am saying, these signals are classified based on dimension, which stands for an independent variable. So, how you are going to classify based on dimension? No? So, one-dimensional signals. One-dimensional signals. They are classified as two-dimensional signals. They are classified as three-dimensional signals. Four-dimensional signals and so on. Four-dimensional signals and so on. Coming to the first classification called one-dimensional signals, the name itself signifies dimension stands for independent variable, and remember, these one-dimensional signals are those signals which will be having only one independent variable. So, one-dimensional signals are those signals which will be having only one independent variable. The best example for one-dimensional signal, what you can give is an audio signal, or for electrical students, it is nothing but a current signal or a voltage signal, an audio signal which we are listening daily, denoted by f of t. F of t. In order to represent this one-dimensional signal, we'll take one vertical axis and one horizontal axis. Along the horizontal axis, we are going to represent the independent variable. And along the vertical axis, we are going to represent the dependent variable. Dependent variable means dependent on this one. And remember, independent variable means it is the quantity of a signal. Independent variable means it is the quantity of a signal which we can vary. Here we can give different values of t along horizontal axis, and we can record the values along vertical axis. This independent variable and dependent variable, they will have some functional relationship, so that as we are going to give different values of t along horizontal axis, we can record the values along vertical axis. So an audio signal typically will be shown like this. So one-dimensional signal means one independent variable. Coming to two-dimensional signals, how many independent variables we can expect? A dimension stands for independent variable. If one-dimensional signals are having one independent variable, naturally two-dimensional signals will be having two independent variables. So these are the signals which will be having two independent variables. The best example for two-dimensional signals, what you can give is a image, what we are storing in a computer. Image. Our friends will be sending many images, no? In the WhatsApp you will be receiving many images. They are all two-dimensional signals. So if you are receiving an audio message, means one-dimensional signal. If you are receiving this kind of picture, means it is a two-dimensional signal. So an image can be taken as an example of two-dimensional signal, denoted by f of x comma y. F of x comma y, two independent variables x and y, where here x and y are known as spatial coordinates. These are known as what? Spatial coordinates. Remember, independent variable need not be time always. Independent variable need not be time always. It can be time, it can be space, it can be frequency, it can be anything based on the application. A two-dimensional signal image is represented like this. We are going to take the spatial coordinate x along horizontal axis and spatial coordinate y along vertical axis. And what I said, independent variable means it is the quantity of a signal which we can vary, I said. In the case of one-dimensional signals, we are having only one independent variable, so that as we are going to give different values of t along horizontal axis, we can record the values along vertical axis. But in the case of two-dimensional signals, how many independent variables we are having? Two independent variables, means you can vary the value of x as well as you can vary the value of y also. Then where you are going to take the value, their intersection gives the value. Their intersection gives the value, denoted by f of x comma y, which is known as intensity. What we call intensity, or the other name is pixel value. Pixel value, which gives some information about brightness or contrast of image. Intensity gives some information about brightness or contrast of the image. Two independent variables, two-dimensional signal. Coming to three-dimensional signals, how many independent variables you can expect? You became masters, I think, by this time. Three independent variables. Three independent variables. These are the signals which will be having three independent variables. The best example for three-dimensional signal, what you can give is a black and white TV picture. Black and white TV picture. I don't know how many of you have seen black and white TV. See, black and white TV picture can be taken as an example. Now, how you are going to represent? Now, if I take two-dimensional signal called image, see, at any instant of time, image is constant, no? Image is a still picture. Image is a still picture. Now, f of x comma y represent what? Brightness or contrast, I said. If brightness or contrast varies with time, three-dimensional signal, three independent variables, three-dimensional signal, right? So if your friend is sending a video message, okay, in which there is a motion, that is nothing but a three-dimensional signal. Now this is about black and white TV picture. Then what about color TV picture? And we know that any color is composed of three components: red, green, blue. Accordingly, we are going to have for color TV picture, intensity of red, intensity of green, intensity of blue. Three independent variables, three-dimensional signal. Coming to four-dimensional signal, how many independent variables we can expect? Four independent variables. Four independent variables. And what are the best example you can give for a four-dimensional signal? I can give like this. Temperature at a point in a room. Temperature at a point in a room. Suppose if I take any point in space, we know that any point in space can be represented with three coordinates: theta of x, y, z, and temperature varies from time to time now. So four independent variables, four-dimensional signal. Now if you observe this temperature at a point in a room, this black and white TV picture or color TV picture, or this image or this audio signal, they all carry some information through. Information is present in each and every category. Or in general, we define the signal as a physical quantity carrying some amount of information. We define signal as a physical quantity carrying some amount of information. Right? Now, one good news is that, sir, you may be getting doubt now. Sir, for examples, you are explaining all this. Do we need to study all this for GATE? No, Baba, there is a good news for you, that for any competitive exam like GATE or IES or any public sector undertakings, we are having only one-dimensional signals in our curriculum, in which we have only one independent variable. We are not concerned with the two-dimensional signals, three-dimensional signals, or multi-dimensional signals. So our focus is towards one-dimensional signals only, in which we have only one independent variable. But if you know the concepts of one-dimensional signals well, you can extend the same to rest of the classification. How? Say, assume that you are going to get a single integral here. You will be getting a double integral here. You will be getting a triple integral here. Say, you have one-dimensional Fourier transform here. You will be having two-dimensional Fourier transform here. You will be having three-dimensional Fourier transform here. So, knowing the concepts of one-dimensional signals is very much essential. So, if you know the concepts of one-dimensional signal, you can extend the same to rest of the classifications. Remember, our focus is towards one-dimensional signals only. So, what is the next job? Let's see the types of one-dimensional signals. Fine. Hope you are all following. So, till now what we have seen? We have seen what is the definition of a signal. That signal is a physical quantity carrying some amount of information. And after that, we classified signal based on dimension, which stands for a independent variable. Remember, signals are classified based on dimension. And we came to a point that for competitive exams, we are having only one-dimensional signals in our curriculum. Now we are going to discuss the types of one-dimensional signals, right? Remember, my dear students, these one-dimensional signals, taking time as independent variable, are classified into three types. Can be classified into three types. First type, continuous time signals. What is the first type? Continuous time signals. Second one, discrete time signals. Discrete time signals. Third one, digital signals. Digital signals. What are these continuous time signals, discrete time signals, digital signals, and what are their interrelationships we are going to discuss now. Coming to the first classification called continuous time signals, in order to represent these continuous time signals, we will be taking one vertical axis and one horizontal axis. Along the horizontal axis, we are going to represent the independent variable, and in the case of continuous time signals, your independent variable happens to be t. And the dependent variable is taken along vertical axis denoted by f of t. And this is a continuous time signal. If this is a continuous time signal, what is the definition of continuous time signal you are going to give? Remember, continuous time signals are those signals. Continuous time signals are those signals which are present throughout the continuous time period. Continuous time signals are those signals which are present for every value of the independent variable. Continuous time signals are those signals which are present for every value of the independent variable. In the sense, the signal is defined at 0, it has some value, some 2.5. The signal is defined at 1, it has some value, some 2.6. The signal is defined at 2, it has some value, 2.52, some value. The signal is defined at 3, signal is defined at 4, and so on. In the same way, the signal is also defined at 0.5, it has some value. No? The signal is defined at 1.5, it has some value. The signal is defined means it will be having some value. The signal is defined at 2.5, it is having some value. The signal is defined at 3.5, it will be having some value. Instead, the signal is also defined at 0.01, 1.01, 2.01, 3.01. Or if you can break the interval from 1 to 2 into 1 crore parts, break the interval from 1 to 2 into 1 crore parts, each part will have some value. That is the definition of continuous time signal. Continuous time signals are those signals which are present for every value of the independent variable. After knowing the definition of continuous time signals, we'll see what is the nature of this independent variable. This is independent variable. No? Independent variable generally will be taking on horizontal axis. This is the dependent variable. We'll see the nature of independent variable and the nature of dependent variable in the case of continuous time signals. So, independent variable nature, dependent variable nature. So, independent variable means it can take any value, right? We can observe the signal at 0, 0.1, 0.2, 1.1, 1.3, any value you can observe. So, I can write here that independent variable is continuous. See, continuous time signal can be defined for any value of the independent variable. Any value means continuous. Now, coming to the dependent variable, which is nothing but your amplitude. Any amplitude you can have. At 0, 2.5, at 1, 2.6. Any amplitude you can have. Means dependent variable. This dependent variable can also take any value. So, it is also continuous. Both independent and dependent variable, they can take any values in the case of continuous time signal. So, they are continuous. Now, after knowing the definition, the nature of independent and dependent variables, the next thing is what? What are the examples you can give for a continuous time signal? A signal represented of the form f of t is equal to e power minus t u of t. The signal represented of the form f of t is equal to e power minus t u of t can be taken as an example of continuous time signal. So, e power minus t u of t means it will look like this. what is this e power minus t, what is this u of t, what is their multiplication, why the signal came like this we are going to discuss in future, but for the time being this signal can be taken as an example of continuous time signal which is defined at every instant of the independent variable, which is defined at every instant of the independent variable, right? So this is about the continuous time signal. Now the next thing is, let's switch to discrete time signal. In order to represent the second category called discrete time signals also, we'll take one vertical axis and one horizontal axis. Here also in the case of discrete time signals, the independent variable is taken along horizontal axis, but it is denoted by n. Remember my dear students, independent variable is denoted by n in the case of discrete time signal, whereas independent variable is denoted by t in the case of continuous time signals, and dependent variable is denoted by f of n. F of n. Now discrete time signal can be shown like this. Right. This is a discrete time signal. If this is a discrete time signal, what is the definition of discrete time signal you are going to give? Remember, discrete time signals are those signals. Discrete time signals are those signals which are defined only at discrete instance of the independent variable. Only discrete instance of the independent variable, not at every instant of the independent variable. As in the case of continuous time signal, see, continuous time signals are those signals which are present at every instant, of the independent variable. Whereas the discrete time signals are those signals which are present only at discrete instance of the independent variable, or in particular we can say integer multiples of the independent variable. Integer multiples of the independent variable, 0, 1, 2, 3, 4, 5, these are all integers, no? So integer multiples of the independent variable. For integer multiples of the independent variable only discrete time signals are defined. So for fractional values, discrete time signal is not defined. Between 2 and 3, 1.5 is there, which is a fractional value. For 1.5, continuous time signal can be defined, but discrete time signal cannot be defined. Only these are defined only for discrete instance of the independent variable or integer multiples of the independent variable. So discrete time signals are those signals which are present only for the integer values of the integer multiples of the independent variable. That is the definition. And after knowing the definition, again we'll see what is the nature of this independent variable and what is the nature of this dependent variable in the case of discrete time signals. So independent variable, dependent variable. Right. What is the nature? Again, what is the definition of a discrete time signal? Discrete time signals are those signals which are present only for the integer values of the independent variable. If this signal would have defined at every instant, as in the case of continuous time signal, we would have said that the independent variable is continuous. But here the signal is defined only for integer values of the integer multiples of the independent variable, not at every instant of the independent variable. No? So we are going to say that the independent variable is discrete. Now coming to the dependent variable, any value you can have. At 0 you can have an amplitude of 2.5 to any amplitude you can have, means dependent variable is still continuous. Dependent variable is still continuous. Right? This is about discrete time signal. The next thing what you can ask is, sir, what are the examples you can give for a discrete time signal? And remember, my dear students, that discrete time signals are represented as sequences. What I am saying? Discrete time signals are represented as sequences where we'll follow this notation. Which notation? This notation. So, and remember, these kind of square brackets are used for representing discrete time signal, and these kind of parentheses are used for representing continuous time signal. Independent variable is t, independent variable is n. And what I'm saying, discrete time signals are represented as sequence. What is a sequence? Sequence is nothing but set of samples. So curly braces open, 1, -2, 1.5, 3. This kind of representation will give for a discrete time signal. After that, we'll place an arrow here. Arrow is the reference point which indicates the sample value at n is equal to 0. Arrow is the, what I'm saying, reference point which indicates the sample value at n is equal to 0. To the right side of arrow are integer multiples of the independent variable. N is equal to 1, n is equal to 2, n is equal to 3. Left side of arrow are n is equal to -1, n is equal to -2 kind of things. In order to represent this discrete time signal, what I am going to do is take the independent variable n. So 0, 1, -1, -2, right? Represent this discrete time signal. What is the value at 0? 1.5. Give a sufficient amplitude of 1.5 in the upward direction. What is the value at 1? 3. Give a sufficient amplitude in the upward direction. 3. What is the value at -1? It is -2. -2 means downward. Okay. This is -2. What is the value at -2? 1. So this is the representation of a discrete time signal. And remember, my dear friends, that in exams, if this arrow is given, well and good. We are happy if arrow is given. But if this arrow is not given, by default you must take the arrow at the first point. Suppose if this kind of sequence is given, f of n is equal to some 1, 2, 3. This kind of sequence is given where he has not specified any arrow. So by default you must take the arrow here. Right? Now after this, after knowing the definition of continuous time signals which exist at every instant of the independent variable, and discrete time signal which exists only at integer multiples of the independent variable, we must see, is there any functional relationship that exists between continuous time signals and discrete time signals? Yes, by a process known as sampling. These continuous time signals are converted into discrete time signals, or sampling is the relationship that exists between continuous time signals and discrete time signals. Now how this sampling is done in a shorter way, and how this sampling is done by multiplying the impulse, and all that we'll discuss later. But for the time being, remember that the relationship between continuous time signals and discrete time signals is sampling. Now after getting a discrete time signal from a continuous time signal by a process known as sampling, what is the nature? What is the nature of this discrete time signal? What is the nature of this discrete time signal? If you observe, independent variable is discretized. Remember, with the sampling, the purpose of sampling is independent variable is discretized. Before sampling, independent variable is continuous. After sampling, independent variable is discretized. Yes or no? And we know that if we want to process any signal in a computer understands only the language of ones and zeros. Now our aim is that we have to convert these continuous amplitudes. Our aim is to convert these continuous amplitudes in discrete case. Our aim is to convert these continuous amplitudes in discrete case to discrete amplitudes. To discrete amplitudes, which is done by a process known as quantization. So I can say that by a process known as quantization, these discrete time signals are converted into digital signals. See, quantization means what? Rounding off. Suppose if you are having a value of 2.5, you can round it to 2, or you can round it to 3, so that you can give the binary representation. Now, can you tell me what is the nature of independent variable And what is the nature of dependent variable? In the case of digital signals, both are discrete. Independent variable is discrete previously only. Now dependent variable is discretized with quantization. Both are discrete. Or I can say that now the digital signal. Not to draw this one. Independent variable. Here, dependent variable, they can take only integer values. This kind of representation we are going to give. Or we can say that these digital signals are nothing but discrete time signals only, but with amplitude quantized. Digital signals are nothing but discrete time signals only, but with amplitude quantized. Electrical students, you need not worry, you don't have this classification called digital signals. EC people will have the three classifications. Electrical people only continuous time and discrete time enough, right? Digital signals are nothing but discrete time signals only, but with amplitude quantized. From this classification, if I ask you one question, if I want to discretize, listen the question carefully. If I want to discretize the dependent variable, to which operation I must go for? Discretize the dependent variable. Dependent variable is taking on vertical axis, or go for quantization. Yes or no? In the same way, if you want to discretize the independent variable means horizontal axis. Discretization means before discretization we have continuous, means continuous time signal must be converted to discrete time signal. So go for sampling. In this way you have to remember. Okay, hope you are comfortable with the classification of one-dimensional signals, and I'll tell you about the sampling. Don't worry. I'll tell you how the sampling process is done, how a continuous time signal is converted into discrete time signal. So, I mean, a lot of discussion is there. Now, the next topic, what we are going to discuss is the transformations of the independent variable. Very, very important topic. Transformations of the independent variable. The whole subject revolves around this topic. Transformations of the independent variable. Transformations of the independent variable. What transformations we can perform on the independent variable of a given one-dimensional signal? My dear students, basically 3 transformations we can perform. They are listed like this. First one is time shifting operation. Time shifting operation. Second one is time reversal operation. Third one is time scaling operation. These are the 3 transformations of the independent variable which we can perform. First of all, we'll do one thing. Individually, we'll be discussing what is this time shifting, what is this time reversal, what is this time scaling. After that, we'll combine all the operations and we'll see what are the available methods and shortcuts we have. So, coming to the first one, time shifting operation. Listen carefully. Very, very important topic. Time shifting operation. How we are going to define this? If x of t represents your original continuous time signal, then its time shifted version is denoted by x of t minus t naught. X of t minus t naught. 2 cases arise here. Case 1, case 2. Case 1 is what happens if t naught is positive. Case 2 is what happens if t naught is negative. Remember, if T naught happens to be positive, the resulting signal, what you are going to get will be a delayed version of the original signal. If T naught happens to be positive, the resulting signal is a delayed version of the original signal. Whereas if T naught happens to be negative, the resulting signal what you are going to get will be an advanced version of the original signal. T naught positive, delayed version; T naught negative, advanced version. Let's check with an example. Okay. Observe here. Suppose I'm having a signal like this, x of t. This is the signal I'm having, x of t, continuous time signal. From this, I want to get what is x of t minus 1 and what is x of t plus 1. If you want to get x of t minus 1, do one thing. Always compare with the standard shift. This is in the form of x of t minus t naught, where the value of t naught is 1. Positive or negative? Positive. If t naught happens to be positive, as per our discussion, the resulting signal must be a delayed version of the original signal. Actually, our original signal has to start at 0. Instead, the resulting signal is delayed by 1 minute. So that it will start at a point called 1. This is x of t minus 1. In the same way, if you want to get x of t plus 1, this is in the form of x of t minus t naught, where the value of t naught is minus 1. Positive or negative? Negative. And as per our discussion, if t naught happens to be negative, the resulting signal what you are going to get will be an advanced version of the original signal. Actually, your original signal has to start at 0. Instead, the resulting signal is advanced by 1 minute, so that it will start at a point called minus 1. This is x of t plus 1. Now, based on this example, what we have seen, can I say one statement that delay means right shift, advance means left shift? What is that? Delay means right shift, advance means left shift. Yes. So simply, I can write here, delay means right shift. Advance means left shift. Delay means right shift, advance means left shift, and the same definition holds good in the case of discrete also. So for discrete, we'll write like this: x of n is our signal, no? So a shifted version is x of n minus n naught. If t naught comma n naught happens to be positive, delayed version, and if t naught comma n naught happens to be negative, advanced version. Delay means right shift, advance means left shift. Now we'll do one thing. As we have seen one example for continuous case, let's see one example for discrete case. Are you ready? I'm ready. Observe here. So I'll take a new page. So look here. One signal is given to you like this. Discrete time signal means how it is represented? Set of samples, no? Sequence. Sequence is set of samples. Right? So in discrete time signals, those here, if you observe here, these are known as sample values. So set of samples is a sequence. Okay, fine. Take one signal. One signal will take like this. 3, 4, 5, 4, 3. What does it require? Can you tell me, can you guess what does it require? The reference point arrow it requires. Here arrow. If arrow is not given, take the arrow at the first point. Okay. Now, try to draw this signal. What is asking first of all, he wants to calculate what is x of n minus 1 is how much? He is asking us to calculate these two, x of n minus 1 and x of n plus 1. First of all, if you want to calculate those, you must draw the signal. No? Remember, my dear students, in our subject, the first task is to draw the signal. Now, Discrete time signal. Discrete time signal, how to draw independent variable, make the independent variable ready. Okay. Arrow indicate the sample value at n is equal to 0. Right side of arrow 1, 2. Left side of arrow -1, -2. So at 0, what is the value? 5. Give a sufficient amplitude of 5 in the upward direction. What is the value at 1? 4. What is the value at -1? 4. This is 4. What is the value at 2? This is 3. What is the value at -2? The first task is completed, representing the signal. So whatever the problem, first of all, we must be in a position to draw the shape of the signal. Right. Now x of n minus 1. X of n minus 1. If you analyze, x of n minus 1 is in the form of x of n minus n naught, where the value of n naught is 1. Positive or negative? Positive. If n naught happens to be positive, the resulting signal must be a delayed version of the original signal. Shift right. Delay means right shift, no? Shift right the given signal by 1 unit to the right. So what will happen in that case? If I shift right, -1, 0, 1, 2, 3. So 3, 4, 5, 4. Now, can you write this in terms of a sequence? Yes. Three, 4. Where you have to place the arrow? Sorry, here. 3, 4, 5, 4, 3, but you have to place the arrow at 4. This is x of n minus 1. In the same way, x of n plus 1. X of n plus 1. First of all, analysis. Whatever the problem, first of all, if you can analyze the given problem, a lot of simplification can be reduced and you can get the answer in one shot also if your analysis is perfect. Okay, in that way you have to develop your subject. This is in the form of x of n minus n naught, where the value of n naught is -1. Positive or negative? Negative. Time shifting operation, n naught positive or n naught negative means delayed version, advanced version, advanced version. Advanced means right shift or left shift? Left shift. So simply shift left the original signal by 1 minute. So -3, -2, -1, 0, 1, 2, 3, 4, 5, 4, 3. That's it. That's it. So can you write this in the form of a sequence? X of n plus 1 is also 3, 4, 5, 4, 3. The arrow placed at this 4. Right? Now, x of n minus 1 I got, x of n plus 1 also I got. Now, based on this, can you make any analysis? Observe, my dear students, that if you are delaying by 1 minute, arrow moves to the left by 1 minute. Observe here. If you are delaying by 1 minute, arrow is moving to the left by 1 minute. If you are advancing by 1 minute, arrow is moving to the right by 1 minute. Very interesting thing, no? Observe here. If you are delaying by 1 minute means arrow moves to the left by 1 minute. If you are advancing by 1 minute means arrow is moving to the right by 1 minute. The same way, if you delay by 2 units, what will happen? If you delay by 2 units, arrow moves to the left by 2 units. So the same sequence will come, but I have to place the arrow here. In the same way, if I advance by 2 units, means arrow moves to the right by 2 units. 3, 4, 5, 4, 3. With the arrow placed at 3. But I understood your doubt. Sir, what happens if I delay by 3 units? That's what is your doubt now. So if I delay by 3 units, means arrow must move to the left by 3 units. If arrow moves to the left by 3 units, nothing is there. In discrete, nothing is there means you can represent with a 0. So, if sample value is missing means you can replace that with 0. 0, 3, 4, 5, 4, 3. Same is with advancement also. In this way, we are going to have this time shifting operation, and hope you enjoyed this one. So, time shifting is done. Let's put a tick mark because we are done with this one now. So, if you are done with this, red color visible by time shifting. Now, let's understand the second operation, transformation of the independent variable, which is nothing but time reversal operation. Okay. For that, I am going to take a new slide. So, time reversal operation. Second transformation of the independent variable. Time reversal operation. How you are going to define this time reversal operation? I can define like this. Observe here carefully. If x of t represents your original continuous time signal, what is continuous time signal? Which is defined at every instant of the independent variable. Definitions you must not forget. Okay. If x of t represents your original continuous time signal, then x of minus t represents the time reversed version. Time reversed version, which is nothing but what? Mirror image along vertical axis. Mirror image along vertical axis. Vertical axis, or this is also known as time reversal, is also known as folding the signal along vertical axis. Folding the signal along vertical axis. With an example, we'll see. Suppose if you are given a signal like this, a continuous time signal defined from 1 to 2. This is a signal. This is x of t. From this, he is asking us to find out what could be x of minus t. So just now we have seen that x of minus t is nothing but mirror image along vertical axis. Now do one thing, you consider this vertical axis to be a mirror. What happens if you consider this vertical axis to be a mirror? If you observe this 1 in a mirror, it will be seen at equidistant point called minus 1 on the other side. And if you observe this 2 in a mirror, it will be seen at equidistant point called minus 2 on the other side, so that the time reverse version is given like this. Time reverse version. Or simply fold the signal on vertical axis. Or just flip the signal on vertical axis. Now, this is x of t, this is x of minus t, fine. Now, my question is, what could be minus x of minus t? What could be minus x of minus t? Now, in order to get this minus x of minus t, first of all, observe these two. Observe these two. What is the difference? Here amplitude is positive, here also amplitude is positive, but time is reversed. Time is reversed. Now, in order to get this one, observe these two. What is the difference between these two? Time is reversed in both. Time is reversed in both, but amplitude is positive here, amplitude is negative here. Now, what is our aim? Our aim is to make this positive amplitude as negative amplitude. So, do one thing. To this time reverse version, take the mirror image along horizontal axis. Take the mirror image along horizontal axis. Minus x of minus t. Or based on this example, can you say one statement that if you want time reversal, take the mirror image along vertical axis. If you want time reversal, take the mirror image along vertical axis. If you want amplitude reversal, take the mirror image along horizontal axis. Let me write that. Time reversal. Time reversal. Mirror image along vertical axis. Vertical axis. Amplitude reversal. Amplitude reversal. Mirror image along horizontal axis. And the same definition holds good in the case of discrete also. X of n, x of minus n. Time reversal means mirror image along vertical axis, and amplitude reversal means mirror image along horizontal axis. Right? Now let's take an example of discrete case also. If you observe, x of n is equal to same previous signal only I am taking, but I am placing the arrow at 4. For this one, calculate x of minus n. Draw x of minus n. Draw x of minus n. First of all, we will try to draw the signal x of n. Zero, 1, 2, 3, minus 1. 0, 1, 2, 3, minus 1. What a value at 0? 4. What is the value at 1? 5. What is the value at 2? 4. 3. This is x of n, discrete time sequence. X of minus n. X of minus n is what do you know? Mirror image along vertical axis. So consider this vertical axis to be a mirror. What happens if I observe this 1 in a mirror? It will be seen at a point called minus 1. 2 in a mirror, minus 2. 3 in a mirror, at minus 3 I will be seeing. 0. Minus 1 in a mirror, you will see it 1. Now how you are going to draw? This one, like this. Three, 4, 5, 4, 3. Now can you write this in terms of a sequence? Three, 4, 5, 4, 3, but you have to place the arrow at. So can you make any analysis for time reversal in the case of discrete? Yes. See, do one thing. This is x of n, no? By observing this one and this one. See, this is x of n, this is x of minus n. So if you want time reversal, do one thing. Keep the arrow or keep the sample value at the arrow as it is, and after that, see, shift the samples to the right side of the arrow to the left, and shift the left side of the arrow samples to the right. Understood what I am saying? Here, in order to get the time reversal, keep the sample value at the arrow as it is. After that, observe the sample values to the right side of arrow. So after observing, you place them on the left side of arrow, and you observe the sample values at the left side of arrow, you place them onto the right. That's it. Suppose if you are given this kind of sequence, 3, 4, 5, 4, 3. This is the original sequence, assume. Now x of minus n, x of minus n means what I said. First of all, keep this as it is. Move the sample values to the right side of arrow to the left, left side of arrow to the right. So left side we don't have any to put them on the right, but we have right samples to put them on the left. So this becomes 3, 4, 5, 4, 3 with arrow placed. In this way you can get the reversal, right? Suppose if you are to take one more example also. Three, 4, 5, say 4, 3. If this is there. Now I want the reversal. Reversal means what you have to do? You have to keep this as constant and move the right samples to the left samples to the right. So 3, 4, 5, 4, 3, the same thing will come. And remember, if you are going to get the same thing, we have a definition. So saying that x of n is even. Anyway, we will discuss that later. But for the timing, as I am getting this one, I am saying that it is an even signal, right? So in this way, you are going to perform the time reversal operation. So what is the next operation? Time scaling operation. Let's look at the next transformation of the independent variable, which is an important one, time scaling. So time scaling. This is the most important transformation of the independent variable among these three. What is scaling? Scaling means multiplying the independent variable by a constant. Scaling means multiplying the independent variable by a constant, and this time scaling operation for continuous time signals. First of all, we discuss continuous time signals. Can be given like this. If the signal x of t represents your original continuous time signal, then its time scaled version is denoted by x of alpha t. Multiplying the independent variable by a constant is known as scaling. Two cases arise here. What happens if the scaling factor is greater than 1, and what happens if the scaling factor is less than 1? Remember, if the scaling factor is greater than 1, the resulting signal, what you are going to get will be a compressed version of the original signal. Compressed version of the original signal. Whereas, if T0 happens to be negative, if alpha value is less than 1, if alpha greater than 1, compressed version of the original signal. Whereas, if alpha value is less than 1, the resulting signal, what you are going to get will be an expanded version of the original signal. Expanded version of the original signal. We'll do one thing, we'll see with an example. Say, we are given a signal like this, a continuous time signal defined from 2 to 4 with an amplitude of 1. This is x of t, from which we are asked to get what is x of 2t and what is x of t by 2. Now, before going to calculate, let's make some preliminary analysis like this. Now, if you observe this x of 2t, this is in the form of x of alpha t, where the value of alpha is what? 2, greater than 1. So, from our analysis, if the scaling factor happens to be greater than 1, the resulting signal must be a compressed version of the original signal. We'll see how that is going to come. In the same way, if we compare this one with x of alpha t, here what is there in place of alpha? 1 by 2, means alpha value is less than 1. So, from our discussion, if alpha value happens to be less than 1, the resulting signal must be an expanded version of the original signal. But how to get the compressed version or expanded version is the question. You can follow this method what I am giving here. See, in order to get either the compressed version or expanded version, do one thing. Always try to divide each point on the horizontal axis with the scaling factor. This is the best procedure. Try to divide each point on the horizontal axis with the scaling factor. Now let's observe what happens. Here in the first case, what is the value of alpha? Alpha value is 2. Here what happens if I substitute 2? Observe here. Okay. What happens if I substitute 2? 2 by 2 is 1. So in the resulting signal 2 became 1. Here what happens if I substitute 2 here in this place? 4 by 2 is 2. Now if you observe, the original signal is going from 2 to 4. Now the resulting signal will move from 1 to 2 with the same value 1. This is x of 2t. X of 2t. Now if you observe, what is the width between 2 and 4 in the original signal? What is the width here? How many units? 2 units. Here what is the width between 1 and 2? 1 unit. So the width has decreased, no? compressed version. Compressed version, or compared to the original signal area, the resulting signal area is decreased. Compressed version. In the same way, come here. How to get this expanded version? This is t, this is x of t by 2. Divide each point on the horizontal axis with the scaling factor. What is scaling factor? 1 by 2. So 2 by 1 by 2 means it will become 4. 4 by 1 by 2 means it becomes 8. So in this way, see, the original signal is going from 2 to 4. Now the resulting signal will move from 4 to 8 with the same amplitude. Now what is the width between 2 and 4? How many units? 2 units. What is the width between 4 and 8? How many units? 4 units. The width has increased, or the area of the signal has increased. So this is an expanded version of the original signal. Right? So in this way you can perform either compression or expansion. Now let's see for a discrete time signal what will happen. Okay. So I'm taking one example for discrete. Known example only we'll take. X of n is equal to 3, 4, 5, 4, 3 with the arrow placed at 5. What is the significance arrow? What is the significance of arrow? Hope you remember. Arrow indicates the sample value at n is equal to 0. If arrow is not given, what do you have to do? Simply take the arrow at the first point. Already we discussed all these points. Now here, given this, he is asking us to find out x of 2n and x of n by 2. X of 2n and x of n by 2. Now, how you are going to perform? How you are going to perform? First of all, try to draw the shape of the signal. How to draw? Here arrow indicates the sample value at n is equal to 0. So right side of arrow are n is equal to 1, n is equal to 2. Left side of arrow are n is equal to minus 1, n is equal to minus 2 kind of things. Right? Now 0, 1, 2, minus 1, minus 2. What is the value at 0? 5. Give a sufficient amplitude of 5 in the upward direction. What is the value at 1? 4. First of all, you must be in a position to draw the shape of the signal. Then you can make any analysis. Okay. What is the value at 2? Is 3. What is the value at minus 1? Again 4. What is the value at 2? It is again 2. This is the shape of the signal x of n. Now, what is that we got? What is that we want? X of 2n. And what I said, in order to get x of 2n, divide each point on the horizontal axis with the scaling factor. Right? Now, in the first case, what is the scaling factor? Here, this is in the form of x of alpha n, where the value of alpha is 2. Scaling factor is 2. Now, substitute and observe what happens. Observe here. Minus 2 by 2. So, this will become minus 1. Minus 1 is integer or non-integer? Integer. Integer values of the independent variable are allowed in discrete, but non-integer values or fractional values of the independent variable are not allowed in discrete. Hope you remember that point. Now, second, what happens if I substitute alpha is equal to here? Minus 1 by 2. Minus 1 by 2 is an integer value? No. So, this will not come in the resulting signal. 0 by 2, 0. Yes, integer. This will come. After that, 1 by 2. 1 by 2 is a non-integer value. So, this will not come in the resulting signal. After that, 2 by 2, 1. Yes, this will come. This is x of 2n. Now, my question is, can you represent this x of 2n in the form of a sequence? Yes, we can represent how. X of 2n is equal to. So in the form of a sequence we are going to represent, because discrete time signals are represented as sequences. Sequence is a set of samples. Sequence is nothing but set of samples. 3, 5, 3 with arrow placed at. Right. Now after getting this one, let's go to x of n by 2. X of n by 2. Now for that I'll go to the next slide. X of n by 2. So this is in the form of x of alpha n. Scaling is done. What is the value of scaling factor? 1 by 2. Right. Now try to divide each point on the horizontal axis with the scaling factor. Okay. So what we are going to do? Our scaling factor is 1 by 2. Minus 2 by 1 by 2. Minus 4 allowed. Minus 1 by 1 by 2. Minus 2 allowed. 0 by 1 by 2. 0 allowed. 1 by 1 by 2 allowed. 2 by 1 by 2 allowed. Yes or no? So 2 by 1 by 2 4. 1 by 1 by 2 2. 0 by 1 by 2 0. Minus 1 by 1 by 2 minus 2. Minus 2 by 1 by 2 minus 4. So everything is allowed here. So let's draw. Minus 4, minus 2, 0, 1, not 1, it is 2, it is 4. This is 3, 4, 5, 4, 3. Right? This is your x of n by 2. Listen carefully, my dear students. Now my question is, can you write this one in terms of a sequence? Yes, why can't we write? X of n by 2 is equal to, sequence with curly braces open. Here, first from the left, always you have to observe from the left. What is first sample value you are able to see here? 3. After that, what happened? See, after minus 4, the next integer value which is going to come is minus 3. Here if you observe, at minus 3 nothing is there. Minus 3, nothing is there means you can represent with a 0. At minus 3, here the signal is not defined. If it is not defined, you can replace it with a 0. So, minus 3, 0. After that, 3, 0, 4, 0. 5, 0, 4, 0, 3. Look here. At minus 3 not defined. So I have taken the sample value to be 0. At minus 1 also this is not defined. So I have taken the sample value to be 0. At 1 not defined. So I have taken the sample value to be 0. At 3 also not defined. So I have taken the sample value to be 0. In this way, you are going to get this sequence. Now, here, one point you can notice, or if I ask you x of n by 3, from the same, if I ask you what could be x of n by 3, always remember, my dear students, if you are going to, look here, if you are going to scale this discrete time signal by 1 by 2, where here in the denominator if you have 2, always remember between the consecutive samples in the original signal, 1 0 came. So here in the denominator what came? 3 came. So the same in the original discrete time signal, between the consecutive samples, how many zeros will come? If denominator is 2 means between the consecutive samples, 1 0. Your denominator is 3 means between the consecutive samples, 2 zeros will come. So here arrow placed at 5. 3, 0, 0, 4, 0, 0, 5, 0, 0, 4, 0, 0, 3. Or you can generalize this. As, suppose if you have x of n by L. X of n by L. Here L is there means what? Between the consecutive here in the denominator we have L means between the consecutive samples in the original signal, how many zeros will come? L minus 1 zeros will come. L minus 1 zeros will come. Very, very important point. L minus 1 zeros will come. Right? Now, observe here, we have seen, if you closely observe, we have seen the definition for continuous time. We have seen the definition for continuous time, but for discrete, I took an example. Now, can you make analysis on this scaling for discrete time signals? Yes. Observe here. In the case of discrete time signals, how you are going to define this time scaling? First of all, example we have seen. Now we are writing the definition. Time scaling operation for discrete time. Discrete time signals. Okay. How we are going to write the definition? Observe here. If x of n represents your original discrete time signal, then its time scaled version is denoted by x of alpha n. Multiplying the independent variable by a constant is known as scaling. Here also two cases will come. First case, what happens if the scaling factor is greater than 1, and what happens if the scaling factor is less than 1. Remember, if the scaling factor is greater than 1, the resulting signal, what you are going to get will not be a compressed version. We won't say compression in discrete, rather we'll use one term known as decimation. What the term we are going to use? Decimation will occur. Decimation means what? Decrease in number of samples. Decrease in number of samples. So, in time scaling operation for discrete time signals, if the scaling factor happens to be greater than 1, the resulting signal will be a decimated version of the original signal. Decrease in number of samples. Shall we verify? Yes, let's verify. Look here. This is the x of n. How many samples are there in the original signal? 1, 2, 3, 4, 5 samples. I calculated x of 2n. Scaling factor is 2 greater than 1. So, as per our discussion, decimation must occur. Decimation means decrease in number of samples. Only 3 samples. Yes, satisfied. Okay. In the same way, what happens if the scaling factor alpha less than 1? We are not going to call by the name expansion. Rather, we are going to use one word known as interpolation. What is the word we are going to use? Interpolation. If decimation is decrease in number of samples, by analogy, can you say what could be interpolation? Increase in number of samples. Increase in number of samples. And remember, this decimation has one more name, downsampling. What is the name? Downsampling. Downsampling denoted by downward arrow. Downsampling means decreasing the sampling rate. Downsampling means decreasing the sampling rate. Sampling rate means what? Number of samples. If decimation is downsampling, what could be interpolation? Upsampling. Upsampling denoted with upward arrow. Right? Now, this is regarding the time scaling operation for discrete time signals. After that, as we are looking at the previous transformation, directly can I go for the answer if a decimation or interpolation is asked? Miss? Yes, why not? Observe here. X of n is equal to x of n is equal to 3, 4, 5, 4, 3 with arrow placed at 5. Now, I want x of 2n. I want x of 2n. So, if you want x of 2n, do one thing. Do one thing. How to get directly without drawing, without putting pen on the paper, directly answer how you are going to get. See, do one thing first of all. Keep the sample value at n is equal to 0 as it is. Keep the sample value at n is equal to 0 as it is. After that, see what is the scaling factor here? Alpha is equal to 2. To the right and left side of arrow, skip or ignore alpha minus 1 samples. Skip alpha minus 1 samples. Alpha minus 1 means 1 sample. So, to the right side of arrow, I am moving to the right side. So skip one sample. So I'll skip this one, include this one. Right? Now to the left side of arrow also. How many samples I have to skip or ignore? 1. Alpha minus 1. So alpha minus 1 means 1 sample ignore. Include this one. 3, 5, 3. Directly you can write. What happens if your scaling factor is 3? What happens if your scaling factor is 3? Now, what is scaling factor? First of all, observe the scaling factor 3. To the right and left side of arrow, ignore or skip alpha minus 1 sample points. So alpha minus 1 means 2. So ignore. 2 means 4 is ignored, 3 is also ignored. So here this will come like this. 5 will remain as it is. Now to the right side, ignore alpha minus 1 sample points means skip 4, skip 3 also. To the left also, alpha minus 1 means 2. Skip 4, skip this 4, skip this 3. So only this is remain. Or if you have any doubt whether this is working or not means, you can test here. So for x of 3n, alpha value is 3. So divide each point on the horizontal axis with the scaling factor. Minus 2 by 3, non-integer value, it will not come. Minus 1 by 3, it will not come. 0 by 3, yes, it will come. 1 by 3, it will not come. 2 by 3, it will not come. Only this sample value will come. Decimation, decrease in number of samples. So for any sequence, the logic what we have seen is going to work. Right? Anyway, I think you know interpolation directly, how to write the interpolated signal. I think you know. So here, x of n by 2. Look here. X of n by 2 means here, in the denominator what I have 2 means between the consecutive samples, how many zeros will come? 1 0 will come. Directly you can write no. 3 0, 4 0, 5 0, 4 0, 3. Directly you can write. Suppose if I ask you x of n by 4. X of n by 4 I ask you. So first of all, first observation is this is interpolated version. Scaling factor is less than 1 means interpolated version. Interpolated version means there must be increase in number of samples. How number of samples are going to increase? Observe the denominator. In the denominator what you have? 4 you have. So between the consecutive samples in the original signal, how many zeros will come? 3 zeros will come. So 3 zeros, 4 3 zeros, 5 3 zeros, 4 3 zeros, 3. Arrow placement. Increase in number of samples which corresponds to interpolation. I hope you are comfortable with this one. After this, look here. After this, what I am going to do is, see, if you are given x of n is equal to 3, 4, 5, 4, 3, 3, 4, 5, 4, 3 with arrow placed at 5. What is that x of n by 2 we got? X of n by 2. 3, 4, 5, 4, 3, in which you replace the missing samples with zeros. So observe here. 3, 4, 5, 4, 3. 3, 4, 5, 4, 3. Look here, my dear students. So, in the previous slide, what we did, missing samples we replace with zeros like this. 3, 0, 4, 0, 5, 0, 4, 0, 3. This is x of n by 2 we got, isn't it? Where we place the arrow at 5. Instead of replacing the missing samples with zeros, you can do one more thing also. Missing samples can be replaced with the previous values. Between 3 and 4 in the interpolation, we can, if you observe, between 3 and 4, here what we did, missing samples I replaced with zeros. Missing samples are replaced with zeros. That's what I have written here. Now instead of replacing missing samples with zeros, we can replace the missing samples with the previous values. Here sample value is missing, replace with the previous value, this one. Here between 4 and 5 sample value is missing, replace with the previous value is 4. Between this 5 and 4 sample value is missing, replace with the previous value. Between 4 and 3 sample value is missing, replace with the previous value. You can do this one also, or you can do one more thing. Missing samples can be replaced with the average of the sample values. Missing samples can be replaced with the average of the sample values. Here 3 and 4 is there, no? So what is the average of 3 and 4? 3.5. 4 and 5 is there. So 4.5. Remember, these are sample values. Sample values. So means sample values, they are denoted along vertical axis. In discrete, see, independent variable is continuous. Dependent variable, what I am going to write are dependent variable values. Okay. 5 and 4, 4.5. Average of the values 4 and 3, 3.5. Right. Now, if you are going to replace, okay, if you are going to replace the missing samples with zeros, it is known as, remember, zero interpolation. It is interpolation only, increasing number of samples, but it is known as zero interpolation. What it is known as? Zero interpolation. When we are going to replace the missing samples with the previous values, this is what is known as step interpolation. It is also interpolation, but step interpolation. Step interpolation. Here, the case where we replace the missing samples with the average of the sample values, it is also known as interpolation, but linear interpolation. What it is known as? Linear interpolation. Unless specified, you must consider zero interpolation. Default interpolation is zero interpolation. In exams, it specifies step interpolation or linear interpolation, you can go for the second and third. But if it is not specifying anything, means default one is zero interpolation. Default interpolation is replacing the missing samples with the zeros. Zero interpolation only. Default. This is default. Right. Now, my dear students, if you observe, we have seen the transformations of the independent variable. Time shifting we have seen, time reversal we have seen, time scaling also we have seen. Now, I'll do a small experiment kind of thing. I want to perform a small experiment kind of thing. Let's see what is that, and we'll try to get some analysis from that. Okay. So, let me change the color first. Go to the next slide. Okay, what is that experiment? Here, I'm going to take two systems. This is the first system I'm going to consider. Second system I'm going to consider like this. And I'm going to connect them in cascade. Hope you are comfortable with cascade connection. If output of one system is given as the input to the other system, it is known as cascade connection, right? Now, the first input here, or the input to the first system is x of t, and this is y1 of t, y1 of t, not y dash of t, y1 of t, and the overall output is y of t. Here, I'm going to give some input-output relationship. The input-output relationship for the first system is y1 of t is equal to x of 2t. X of 2t means what? Compressed version. Y of t, the input-output relationship between for the second system is y of t is equal to y1 of t by 2. Expanded version. Right now, I think you can notice here y1 of t is an output of the first system, which forms an input to the second system also. Okay, fine. Now, let's apply some input and observe the output. In one input only I apply, or the input what we have seen. This input I apply. This is my x of t. Can you tell me what is my y1 of t? Y1 of t is x of 2t. X of 2t means compressed version. So divide each point on the horizontal axis with the scaling factor. what is that I am going to get? So 2 by 2 is 1, 4 by 2 is 2. This is my y1 of t, right? Now this y1 of t is the input to the second LTI system. What is the output we can expect here? Scaling factor is 1 by 2, 1 by 1 by 2 is 2, 2 by 1 by 2 is 4. The resulting signal will come like this. Now observe the overall input-output relationship. Observe the overall input-output relationship. Yes, they are same. Means we are happy because whatever the signal I am going to give here, and the same thing I am going to get there. So means I am happy. Now let's do one thing. Let's interchange these two systems and observe what will happen. Okay, let's interchange. Means reverse. Okay. So this is my x of t. Now this is my y1 of t. This is my y of t. Now we'll see whether we'll be happy or not. When we'll be happy? When we will be happy, if the input I'm going to give here the same thing if I'm going to get here, I'll be happy. Otherwise also happy, because we are going to make some analysis. Y1 of t is equal to x of t by 2. Here first compression, next expansion. Here first expansion, next compression. Y of t is equal to y1 of 2t. Now let's apply some input and observe the output. So 2 to 4 you apply. This is x of t, right? What could be y1 of t? Y1 of t is expanded version, no? Expanded version, how to get divide each point on the horizontal axis with the scaling factor 2 by 1 by 2, 4, 4 by 1 by 2, 8. Okay, this is what I am going to get here. This is y1 of t. Now this is y1 of t, this is x of t. Now this is given to second system. So here y1 of 2t means divide each point on the horizontal axis with the scaling factor 2 to 4. Yes. This is my y of t. Now if you observe, this is the input I gave and the same thing I got. I'm happy now. Right? This is for continuous. For continuous. Let's observe for discrete. Discrete. So for discrete also, what is the difference between a continuous time signal and discrete time signal? Do you remember? Continuous time signal means they exist at every value of the independent variable. Discrete time signal means they exist only at discrete instance of the independent variable or integer multiples of the independent variable. Definitions you should not forget. Now here in discrete also I am going to take two systems, putting them in cascade. Output of one system is connected as the input to the other system. This is my x of n. This is my y1 of n. This is my y of n. Overall output. Right? Now the input-output relationship of the first system is y1 of n is equal to x of n by 2. What is x of n by 2? Interpolation. If nothing is specified means zero interpolation. Replacing the missing samples with zeros. Now here y of n is equal to y1 of 2n. Decimation. Decrease in number of samples. Let's apply the input and get the output. Known input only I am taking here also. So known input is 3, 4, 5, 4, 3. What is y1 of n? Replacing the missing samples with the zeros, 9 samples will come. Already 5 are there now. So between every two consecutive samples, 1 0 will come. Totally 9. 3 0, 4 0, 5 0, 4 0, 3 with the arrow placed at 5. Now y of n. Y of n is y1 of 2n. And what I told you to how to get this decimated version directly. So to the right and left side of arrow, skip, ignore, neglect How many sample values? Alpha minus 1, scaling factor minus 1. Scaling factor is 2, means neglect alpha minus 1, means observe here. So here to the right side, skip this one, include this one. After that, skip this one, include this one. To the left also, alpha minus 1, skip this one, include this one, skip this one. So what is your y of n? 3, 4, 5, 4, 3. Are you happy? I am happy because the input what I gave here, the same output I got there. Next task, interchange. This is my x of n. This is my y1 of n. This is y of n. So what is the input-output relationship of the first system? Interchange means first decimation will come. Y1 of n is equal to x of 2n, and here y of n will be equal to interpolate y1 of n by 2. Give the input as the same standard input we are going to take. 3, 4, 5, 4, 3. What is y1 of n here? Y1 of n would be to the right and left side of arrow. Skip alpha minus 1 sample values. Alpha minus 1 means scaling factor is 2, 1 sample value. Neglect this one, include this one. Neglect this one, include this one. So 3, 5, 3. Now y of n, interpolation. So you have not specified any type of interpolation, means default interpolation, zero interpolation means wherever the sample value is missing or wherever the signal is not defined, replace that with 0. So between the consecutive samples, 1 0 will come. 1 0 will come. 3 0 5 0 3. Between the consecutive samples, 1 0 will come. Now if you observe the overall input output relationship here, I am not happy because input and output are different. Input and output are different. Now from this example, what analysis you are going to make? Observe here. Now this is continuous time. First of all, what you are doing? First of all, you are compressing. After that, you are expanding. Here, expanding. After that, you are compressing. You are going to get the same signal. Or I can say that in continuous time, inverse of compression is expansion. Inverse of this. What is this operation? Compression. No? Inverse of compression is, see, I'm going to get the compressed signal. Again, if I want to get the original signal, means allow it to expand. So inverse of compression is expansion. Inverse of expansion is compression, because we are going to get the same output what I am going to give as input here, right? So in continuous case, inverse of expansion is, inverse of compression is expansion. Inverse of expansion is compression. Important point, my students. Whereas in discrete, inverse of interpolation is decimation. Inverse of interpolation is decimation, whereas inverse of decimation is not interpolation. Inverse of decimation is not interpolation. So let's make a note of that. Observe. So in continuous time, inverse of compression is expansion. and vice versa. Inverse of compression is expansion and vice versa. Whereas in discrete time, inverse of interpolation is decimation, but the converse is not true. But inverse of decimation is not interpolation. It's not interpolation. These points we have to remember. Anyway, after some time, while discussing systems also, I'll try to prove this one in a different way. But for the time being, you try to remember this. Right. And before going to look at the next kind of operations, can I say one statement that, look here, in continuous or discrete also, no problem. What is scaling? Scaling means x of t, here x of alpha t. This is what is known as time scaling. What happens if alpha is minus 1? What happens if alpha is minus 1? This is nothing but x of minus t, which is nothing but reversal, no? So remember, if you want reversal, scale by minus 1. Time scaling by minus 1 is nothing but reversal. So if the scaling factor is minus 1, it is time reversal. Time reversal. Okay. Time reversal is time scaling only where the scaling factor is minus 1. Remember, minus 1. Now, the next thing what we are going to discuss is very, very important as far as subject is concerned and examination is also concerned. How to get listen carefully, x of alpha t plus beta. How to get x of alpha t plus beta from x of t is a discussion now. Means sometimes they'll give the signal x of t and they'll ask you to get the transformation x of alpha t plus beta, in which we have shifting as well as scaling both. Now, how to perform this one? How to perform or how to approach this one? Now, for this, what I am going to do is look here. So, say I am considering, first of all, we'll try to get the analysis. After that, I'll give the statements. If you follow the statements, you will get the solution for any problem. Right? Now, observe here. Say if I have a signal like this, which is defined from T1 to T2. T1 to T2. This is my signal x of t. Assume that. This is the assumption. Now, from this signal, we want x of alpha t plus beta. X of alpha t plus beta. Before getting this one, observe here, my students, small example. Suppose if I have a signal 2 to 4, x of t. Okay. If I want to get x of 2t, from this signal, what I said, divide each point on the horizontal axis with the scaling factor. One more way is, look here. If you want to get x of 2t, look here, if you want to get x of 2t from x of t, means we have to draw x of 2t versus t. Look here, or the given one is x of t versus t he has given. X of t versus t has given. Now we have to get x of 2t versus t. So do one thing. X of t is defined between what values? X of t is defined between 2 to 4. X of t is defined between 2 to 4. Now if you want to get x of 2t, replace this t with 2t. Replace this t with 2t. This is one more way of getting, or 1 less than t less than 2. So x of 2t is defined between 1 to 2. X of 2t against t is defined between 1 to 2. Like this. This is same as the compressed version, no? Right? Now, he has given, observe here, in this problem, okay, in this problem what he gave? X of t versus t he gave. X of t is the dependent variable, independent variable is t. Now, what is asking us to get? X of alpha t plus beta versus t is asking us to get. Right? Now, what I said, see, compare. First of all, observe the limits where this x of t is defined, 2 to 4. Here x of t, t1 to t2. So, t1 less than t less than t2. Right? Now, if you want to get x of 2t, what I said, replace this t with 2t. If I want to get x of alpha t plus beta, what I have to do? Replace this t with alpha t plus beta. Now, get the limits. Try to get the limits in terms of t. Solve for t now here. Here also we have to get the limits in terms of t. How to get? So there are two ways. Two ways I can find. First way is, observe here. So I must get t here. Instead of alpha t plus beta, I must get t here, because alpha t plus beta we have to draw against t. Right. Now how to get? So how to solve this inequality? First of all, what I'll do is, look here. I'll subtract beta, first method. So t1 less than, again I'm writing here, alpha t plus beta less than t2. See, I'm performing some analysis here. After that, I'll give the statements. If you're not comfortable in following this one, if you can follow statements also, you'll get every problem. Right. Observe here. So here, first of all, subtract beta, t1 minus beta less than alpha t less than t2 minus beta. Now, we must get x of alpha t versus t. No, here t must come. So, divide both sides with alpha. So, t1 minus beta by alpha less than t less than t2 minus beta by alpha. Right? So, limits I got. X of alpha t plus beta lies between t1 minus beta by alpha to t2 minus beta by alpha. This is one method. Other method is, look here. t1, first of all, right, alpha t plus beta less than t2. Now, here take alpha common. Now, divide with alpha. t1 by alpha less than t plus beta by alpha less than t2 by alpha. After this, now what we have to do? Now, do one thing. Subtract beta minus alpha. So, here I am writing. Let me set the pen. Here I am writing, observe here. What happens if subtract beta by alpha? Here and here. Subtract beta by alpha. t1 minus t1 by alpha minus beta by alpha. t1 minus beta by alpha less than t less than t2 by alpha minus beta by alpha. t2 minus beta by alpha. Now, if you observe, same limits we got t1 minus beta by alpha less than t2 minus beta by alpha, t1 minus beta by alpha less than t2 minus beta by alpha. So these are the two methods which you can follow to get x of alpha t plus beta from x of t. Sir, we are facing difficulty in following these expressions. Can you give in terms of statements? Means I'm going to do that one only. But before that, if you observe same values, same here t lies between these two values, here also t lies between these two values. But here what I have done, here I'm subtracting here. I'm subtracting and adding means here first of all I'm doing shifting. First of all shift. And I'm dividing with alpha means then scaling. First shifting, then scaling I'm doing here. Here what I'm doing, first of all, after taking this alpha as common, I'm dividing means here first of all scaling I'm doing. Here scaling I'm doing. After that I'm subtracting something means what? Shifting. So the two methods which are available to get x of alpha t plus beta from x of t is first shift then scale, first scale then shift, first shift then scale, first scale then shift. So let me summarize like this. Note, very important point. Even if you don't understand the previous one, if you understand, if you're going to follow my statements, yes, any problem will come. To get x of alpha t plus beta from x of t. First method. What is the first method? First shift, then scale. First shift, then scale. Okay. So I can give like this. Now we have to get x of alpha t plus beta from x of t. Listen carefully, my dear students. Our aim is to get x of alpha t plus beta from x of t. From the previous procedure, what we have seen, we are going to summarize. So first shift then scale. Start with x of t first. Start with x of t. Observe the shifting factor. Okay. Observe. First shift the signal x of t by beta to get x of t plus beta. After this, do one thing. Consider this shifted signal to be y of t. Consider this shifted signal to be y of t. After that, you simply scale this y of t by alpha so that you will get x of alpha t plus beta. X of alpha t plus beta. So, if the given transformation is in the form of x of alpha t plus beta, which involves shifting as well as scaling, first shift the signal x of t by beta to get x of t plus beta, and you consider this shifted signal to be y of t. After that, you scale this y of t by alpha so that you get x of alpha t plus beta only. With an example, we'll see, don't worry. Suppose if you are given a signal like this, 2 to 4. This is x of t, from which we are asked to get x of 2t plus 4. Right? Now, if you observe, this x of 2t plus 4 is in the form of x of alpha t plus beta. Now, the path is, according to our discussion, x of t is there with you. Okay. So, first shift, what is the in place of beta? 4. So, go to x of t plus 4. Call this as y of t. You scale this y of t by alpha, that is 2, to get x of 2t plus 4. 2t plus 4. Now, let's draw. X of t is there with us, the original signal. These are very powerful methods. X of t. x of t plus 4. X of t plus 4 means, as you know, advanced version. Advanced version means left shifted version. Left shifted version means 2 will go to minus 2. Sorry, yes, 2 will go to minus 2 and 4 will go to 0. This is x of t plus 4, and we consider this to be y of t. This is y of t. For this y of t, what I have to calculate? Y of 2t. Y of 2t means scaling. Divide each point on the horizontal axis with the scaling factor. Minus 2 by 2 means minus 1, 0. This is what you are going to get. So this is x of 2t plus 4. This is the first method. Now, second method. First scale. Don't worry, we are going to solve many number of examples so that you people get confident. First scale, then shift. First scale, then shift. I can give like this. If the given transformation is in the form of x of alpha t plus beta, which is a required one, and if you want to first scale then shift, here you have to take this alpha as common. You have to take this alpha as common. Taking alpha as common here is mandatory, compulsory. Now what is the path? The path is like this. Start with x of t. First scale x of alpha t. After that, here you may have plus, you may have minus also. If you have plus, advance. If you have minus, delay. By what factor? Beta by alpha. Beta by alpha. Now we'll do one thing. We'll see whether this is working or not with respect to the previous example. What is the previous example? This is x of t, from which we need to get x of 2t plus 4. Right? Now, first of all, x of 2t plus 4 means, first of all, you have to take alpha as common. No. First scale then shift means taking alpha as common is mandatory. Remember. Now, the path is start with x of t. Start with x of t. First scale. Scaling factor is 2 here. Go to x of 2t. After that, plus is there. Plus means advance. By how many units? 2 units. Now, x of t is there with us. The original signal. Right? X of 2t. X of 2t means 1 to 2. Divide each point on the horizontal axis with the scaling factor. Compressed version. This is x of 2t. Now, you have to advance this by x of 2t. After getting x of 2t, you have to advance this by 2 units. Advance means left shift. Now, what is the left shifted version of what is the left shifted version of this 1 by 2 units? So, it will go to minus 1. 2 by 2 left shift. This must be your x of 2t plus 4. X of 2t plus 4. Now, let's verify whether we got the same answer or not. So, previous slide. Yes, perfect answer. Perfect answer. Isn't it? So, first shift then scale, first scale then shift. Remember, for first scale then shift, you have to take this alpha as common. And first shift then scale, you have to follow this procedure. So, these two methods will save a lot of time in your exam. And let me tell you, we are going to solve more number of examples based on these two methods.